In the case now where drag is proportional to v squared, we obtain this equation, which has a solution that we've seen to satisfy this condition, provided v is less than square root of f over c. And we can note now that f over square root of f over c is the terminal velocity, so that this is the equation whenever v is less than terminal velocity. That leads us to the solution v equals, well, I'm not going to read it to you, this solution that we've already seen. Then if v naught equals 0, we've determined that this constant a has to equal 1, and we're going to look at the consequences of that. So if v naught is 0, then our constant a is 1, and our solution can be written as square root of f over c times 1 minus this exponential over 1 plus this exponential. Now the square root of f over c is our terminal velocity, so we're going to understand this coefficient out here is our terminal velocity. This expression here is 1 minus a quantity divided by 1 plus a quantity, so it's always going to be less than 1, meaning that our velocity is going to be less than our terminal velocity for every value of t, so that v is going to approach terminal velocity from below. Now, does v approach the terminal velocity? Yes, as t approaches infinity, this exponential having a negative coefficient, the exponent having negative coefficient of t is going to approach 0. So both of these exponentials are going to approach 0. We're going to approach 1 over 1, which means that this whole term is going to approach 1, and our velocity will approach the terminal velocity. So we'll note that as t approaches infinity, and I don't know if we have that in there, v of t approaches our terminal velocity, which is of course what we expect from solutions we've seen for linear drag forces. The same idea of terminal velocity is going to apply to drag forces that are proportional to the square of the velocity. Now, I want to look at this expression in a couple of ways. First, 1 minus e to the negative 2 squared of fc, etc., is going to be a function which has value 0 when t, or has value 1 when t equals 0. I'm sorry, it's going to have value 0. The numerator is going to have value 0 when t equals 0. The denominator will have value 2 when t equals 0. Now if we look at the numerator function, it starts at 0, and as t approaches infinity, approaches value 1, so that we expect this graph to have this characteristic. And in fact, if you flip this graph around the line y equals 1, you get something that looks like a decreasing exponential function approaching 1 as its asymptote. The denominator function is going to start at 2 when t equals 0, and it's going to be approaching y equals 1 as t approaches infinity. So that this expression is this function divided by this function. How do we get a graph of one function divided by another? If we have the graphs of the two functions, we can construct this graph, at least approximately. About here, right around here, I'll note that the value of this function here is about half the value of this function. That is, this distance is about half this distance, which means that this divided by this is about 1/2, and that's going to give us a velocity solution that's 1/2 of the square root of x over c, which we've seen to be the terminal velocity, so that at this value of t, we have this point on the graph. Now, of course, when t equals 0, this function, which is our numerator function, is 0, so we have this point. And as t approaches infinity, these two graphs both approach the same value, so that this expression is going to approach value 1, and velocity is going to approach the terminal velocity. So the terminal velocity is going to be a horizontal asymptote. We're going to start at 0, go through this point, and approach the terminal velocity as an asymptote. We could evaluate this function as a fraction of this function for a number of different values of t and get an even better picture of what the graph looks like, but this graphical illustration of the nature of this ratio here should be helpful. And this also gives us the intuitive idea that the velocity, and this is the velocity versus t, that the velocity function approaches its terminal velocity with a decreasing slope, meaning that you have less and less acceleration as time goes on, and that's exactly what we would expect from a drag force that's proportional to the square of the velocity. The faster we go, the more drag force we have, and the less quickly we change our velocity. Okay, I'm going to do an intermediate rearrangement here. I'm simply going to divide both the numerator and the denominator by e to the square root of fc over m times t. Actually, let's multiply the numerator and denominator by e to the square root of fc over m times t. I'm not going to write that out. I'm just going to write out the result, and it should be fairly easy to see that this is going to give us e to the square root of fc over m times t minus e to the negative square root of fc over m times t divided by, denominator has to be multiplied by the same quantity, e to the square root of fc over m times t plus e to the square root of fc over m times t. And this function, this numerator function divided by 2 is our hyperbolic sine function. The denominator divided by 2 is a hyperbolic cosine function, so that what we have here, and I've written it wrong, it's not the hyperbolic cosine, is the hyperbolic tangent function. So that if v naught equals 0, v of t is equal to v term, the terminal velocity, multiplied by the hyperbolic tangent of, I shouldn't have written the negative 2 there either, square root of fc over m times t. So this whole line should just be obliterated. We see that v of t equals this, and that this function is just a hyperbolic tangent of the square root of fc divided by m multiplied by t. This makes a good bit of sense. Our hyperbolic sine of t has a graph that looks something like this. The hyperbolic cosine of t has a graph, and let's draw that in a slightly different color, that looks something like this. Now, as we go to the right, both of these graphs approach the graph of e to the t divided by 2. So if we had, well, I'm not going to draw that graph in here, but these both approach the same graph as an asymptote, so they're going to come together as closely as we might wish, so that as t approaches infinity, the ratio of these two functions is going to be 1. So if the hyperbolic tangent is going to approach 1, and again our velocity is going to approach our terminal velocity.